record this. So the assignment 4, I extended the due date until, I want to say, Wednesday, so tomorrow at midnight. So assignment 4, assignment number 4, which is on that old stuff, which we're not kind of going back to, but in case you wanted an opportunity to bump up your mark, maybe, is now due Wednesday, February 24th at 11:59 p.m. So I extended it, but then I thought, oh, that's not really fair to people who had done it for the original due date. So what I decided to do is, if you did it for the original due date, I'll bump up your grade by 2 grades or 2 marks out of 8. That's pretty good. So if you got 6, I'll bump you up to 8, etc. Even if you do it again, I'll still bump you up if I have a record of everyone who did it on time or kind of the original due date, so I'll just bump you up. Whatever your grade is by Thursday morning, I'll bump you up by 2 marks, and I think feels fair. So if you have 8 already, you did it on the original due date, then you get 10 out of 8. Tempting. So, all right. Anyways, another thing, I had a lot of time to think over reading break. Oh, I have a different desk. So now it's not just white space. You can't really see, but succulents. They're Jared's succulents. I'm not the green thumb between the two of us. He is, so I'm in charge of keeping them alive until he gets back, and it's not going very well so far. I know they're just succulents, but it's not my cup of tea. So they needed some more light, I think. I don't know. So here we are. Not just white space anymore. Ooh, succulents. All right. So, oh yeah, what was I thinking about? I've decided that it is a cumulative final exam, and I forget to water most of the time, so yeah, hopefully, yeah, the ambiance. I know it changes everything, right? Yeah, someone suggested I could have floating shelves with more succulents. But anyways, might be fun to play around with. Oh yeah, so what I decided was I don't often have a ton of people coming to my office hours. In fact, I can count on one hand how many people have showed up this whole term so far. So instead of me sitting here and just kind of well, doing work, but just kind of staring at a blank screen, office hours, I've decided to make them just by appointment. I'm available on short notice most of the time. So really anytime that you need me, just let me know. But I do want to give you the heads up. I'll post it at the top of our Moodle page as well, where I have my office hours. I'll also post my schedule so you know when I'm teaching other courses, because of course I can't meet you when I'm teaching other courses. But so a change is that office hours are now by appointment. Anytime, any day, which is kind of exactly what it was before. So nothing's really changed there, but so just feel free, and I'm usually available on short notice, right? So I am usually available. It's usually, that doesn't really look like usually. Usually, I have to get used to writing again, a whole week off. It's not as bad as summer, after summer. Ugh. So I'm usually available on short notice. All right, so just let me know, and we can just hop on here and work on whatever you're working on, okay? But it just felt like kind of a waste of time for me to have these strict times where I was sitting here and no one was coming. But I do want to meet with you if you have any questions, so just let me know. Okay, so I sort of lied in my announcement that I sent out. I can't remember if it was yesterday or the day before, but I think yesterday. We start simple interest next day. First, we have to lay some ground rules. So today we have to talk about exponents as well as logs. So exponents and logs are what we're going to use to solve for x, right? So kind of a lot of those math jokes, hey, solve for x, yeah, that's what we're going to be doing. So we'll need to know how to work with exponents. We've actually talked a little bit about exponents already, so but we'll expand on some exponent laws and also log laws, which is fun to say. From Arrested Development, if you've seen it, Bob Loblaws log is what it always makes me think of, the log laws. Anyways, we'll get there. So we're going to start chapter 4. Chapter 4 is on simple interest. I also want to give you kind of an overview of where this course is headed, because I keep promising you that things will get better. Once we start simple interest, once we start interest problems, things will get better, and I promise they will. Because now we're just going to start a concept and then we're going to just slowly build on it for each chapter. Okay, and so kind of an overview first is, okay, so for interest, there are two different types of interest. So simple interest is you put money in the bank and then at the end, they give you some amount of interest, right? So when you take it out, they give you some amount of interest. That would be simple interest. Usually what we're dealing with is compound interest. So which is chapter 5. Chapter 5, we get into compound interest, which is just going to be the idea of, okay, so we compound on some schedule. So every month, for example, the bank checks in and says, how much interest do we owe them? And then you add that onto the initial amount that you invested, and then you're earning interest on the interest that you've made, right? So it's going to be compounding. Okay, so so for interest, right, we're going to have two different kinds. There's simple interest or compound interest, and those are the only two, right? And so here, this is going to be chapter 4. Oops. And compound interest is chapter 5. Okay. From compound interest, what we're going to find is that we could have compound interest with regular payments. And so if you're thinking a car loan, a mortgage, those are our typical kind of financial things that we deal with, right? And so we call those annuities, but they're also going to have compound interest. And so from compound interest, we could have no regular payments. No regular payments. I don't really know when that would happen. Usually we do have regular payments, and so this is chapter 5. And then here we might have with regular payments. And that's going to be chapter 6. So if you have regular payments, we call those annuities. Okay. And then if those regular payments are at the end of each month, then, or each year, or at the end of the payment schedule. So if they're at the end, oh, sorry, I guess I should specify payments at the end of the payment period, we call these regular annuities. I think they're regular ordinary annuities, something like that. Let me just make sure I get the terminology right. It's been a while here. I think it's ordinary annuities. Yeah. This is an ordinary annuity, which is still in chapter 6. So the regular payments are introduced in chapter 6, but so this is chapter 6. And then if the payments, so the only thing that changes from chapter 6 to chapter 7 is that, okay, well, what if the payments are at the beginning of the payment period, right? Things change a little bit financially because you're making a payment sooner, right? But that's the only change that we make from chapter 6 to chapter 7. So you can see how we kind of pick up the pace a little bit there. And so here, if the payments at the beginning, of course, of the payment period, but I don't have space to write that, then we have an annuity due is what it's called. An annuity due, which is chapter 7. Then in chapter 8, we only do one section in chapter 8, and it's on mortgages, and it can kind of, it draws from chapter 6 and chapter 7. It can come from either one of those, and then we do chapter 8 here. So mortgages, which is chapter 8. So you can, well, now let me zoom out just a little bit. So we're going to start here. We're going to develop these ideas, these ways of solving these problems. And then what we're going to do once we get into compound interest, once we introduce that idea, then we stick with that idea, and we're just adding on little changes, right? So here we have no regular payments, and then we go to, okay, well, what if I make monthly payments, right? Which is pretty typical. And then I make the change, okay, well, what if the payments aren't at the end of each month? What if they're at the beginning of each month, right? And then we move on and we dissect some mortgage payments, right? So what are they at each level? And then that's where we end the course. So you can see it all kind of ties together from this point onward. Okay, that doesn't mean it's easy. It just means that there's going to be something to build on every time. So, but before we can start, we do need to talk about exponents and logs. So that's what we're going to talk about today. And of course, as the textbook likes to do, it's called the basics. So kind of in your face, isn't it? So that's our roadmap. And what you'll see if we go to your formula sheet, now where's that formula sheet? Here we go. Right? Notice that we've got, okay, simple interest. This is chapter 4. And then we said, okay, we're going to introduce compound interest. Compound interest, notice that from the tree that we just made, it kind of sticks with us the whole time, but the only problems that we call compound interest are the chapter 5 ones. And of course, that'll make more sense when we get there. So then we've got compound interest, and then if you flip to this nasty part of the formula sheet, right, the back page, then I'm going to leave the first 4 or the top, I guess, 5 formulas, but here, this is chapter 6. And then if they have a little subscript due, right, then we're at an annuity due, and that's chapter 7. And then we actually don't need any formulas for chapter 8 because they'll all be introduced already in 6 and 7. So that's the breakdown of the formula sheet, just so you can kind of see where things are headed, right? Kind of break them down. And as we chip away at this formula sheet, you'll see it's not as bad as it looks. Okay, so let's see here. Okay, so today we're going to establish our basics and just kind of basic kind of math rules that we need in order to be able to solve these problems. So 4.1 is called the basics. I'm sure I've made a big deal about it already, but we're actually not doing 3.1 and 3.4. We're not covering monopolies. It's fun to read through if you have time, but it's not something that's going to be on the final or anything. So I decided to cut it so that we can just stay on schedule. All right, so the basics. We need to talk about exponents, which are just powers, and then we'll switch gears. Exponents, which are just powers, right? Then we'll switch gears to logarithms. So if you have 2 times 2 times 2, well, that's 2 multiplied together 3 times. What you can do is you can rewrite that as 2 to the power of 3, right? So here I'll say recall, and hopefully it is kind of remember this. 2 times 2 times 2, you can rewrite as 2 to the power of 3, right? Or in general, right, what we say is if you have a times, or in general, a times a times a, and then I'll do kind of this, what's it called? It's not ellipses, it's when you're multiplying. Anyways, I can't remember, but right, and we're going to say we're multiplying together n times n a's. Okay. Well, that's the same as saying a to the power of n. Okay, and just for some terminology, right, we've got the base is a, right? So whatever is being multiplied is the base, and then the power is n, or the exponent is n. So where a is the base, and n is the power or exponent. And I use those interchangeably, so just make sure that you're on board with okay, power, exponent, they're the same thing. So we need that terminology, right, for the exponent laws that I'm about to introduce. And so there are rules for working with exponents, and we're going to find them useful for simplifying things. So if you have, so just kind of briefly, if I write 5 times 5 times 5 times 5 times 5 times 5, right, and I ask you to simplify that, well, if you had to simplify this, you'd have to count how many 5s you have. 1, 2, 3, 4, 5, 6. And so here you have 6 5s, if that makes sense. So my base is 5, which I'm going to write down, and then to the power of 6. Okay. Or the other direction, if you have 2 to the power of 4, and you had to expand this out, what does that mean? Well, it means that this is 2 times 2 times 2 times 2. Of course, your calculator can do these powers, any powers. And let's use your calculator. And oh yeah, I have it on here. Okay, I'll use this free one, BA Calc. Uh-oh, likes to go this way. Okay. Do you see what I see? Oh yeah. So over the 9 button, see this y to the power of x button? So what you have to have is you have to have your base on the screen already, right? So 2, for example. And then if you hit y to the power of x, what's confusing about this one, it doesn't show you that it doesn't acknowledge that you've hit the y to the power of x. You just have to kind of go with it. And then you do whatever the power is. So 4, and then equals. So it's going to be 16. Okay. So let's just write that down, just because it's going to be important, right, on your calculator. On your calculator. And you'll want to make sure that your calculator, or that you know how your calculator works, right? Hopefully you have some version of this financial calculator. So what we need is we would have to hit the 2 button. And then there's a y to the power of x button. And then hit the 4 button, and then hit the equals button. And it should give you 16. Okay. Just for some practice, let's do 5 to the power of 6, right, on your calculator. And just make sure that we get the same answer, right? You don't want to be, not now. So clear. And we're doing 5 to the power of 6, just to make sure that we get the same thing. So 5 to the power of 6. So you do the 5, and then the y to the x, and then the 6 equals. You should get 15,625. We can try, and I'll try to keep track of how many 5s I'm multiplying together. I want to multiply 5 together 6 times, and let's just check. Let's just make sure it works. 5 times 5 times 5 times 5 times 5 times 5. Okay, it works. Right, so it's working as we expected it to do. So just make sure that you know how to work your calculator here. So I'll do 5 to the power of 6 equals, so 15,625. $15,625 on your calculator. Okay. So just make sure that you have those under control. So when we're working with exponents, there's going to be a lot of rules for exponents, or exponent laws, let's call them, just to really hammer home that it's important. So when working with exponents, we need to be fluent with exponent laws. We need to be fluent. Oh, it doesn't really read well, does it? We need to be fluent in exponent laws. Okay. Oh, I guess I shouldn't do a colon here. That's just a fact. And then on the next page, I'll put our actual exponent laws. So exponent laws, or we might call them rules of exponents if you want. In my version of the textbook, they're on page 92. Let me just make sure, because they might have changed some stuff. Probably not really, but page 92 of text, if you want to have them to refer to there. But what I want to do is I just want to work through these exponent laws and just kind of talk around them. And hopefully as we do that, then you'll kind of start to feel a little bit more comfortable working with these exponent laws. So the first thing that we're going to use is A is going to be our base, or a base, and N is going to be our exponent. So the first thing we have to establish is that we're going to let A be greater than 0. We have to make the base positive, because otherwise it'll mess with some of the properties. So we're going to let A be greater than 0. Okay. And if you're looking at the textbook, it does say, I'll just copy out what the textbook says here. Let A be greater than 0, and it says it just like this. And M and N are in the set of real numbers. So here, base must be positive. And what we'll find is that M and N are the exponents. So exponents, and I guess I should include set notation, exponents can be any real number. Oops. Any real number. Okay, so that's all that's saying. I know it looks weird, but you kind of just need to talk through it. So, all right. Are we ready to establish some exponent laws, or rules of exponents? Okay. The first one is that, oh, and I guess I should say that a real number is any number between negative infinity and positive infinity. I'll do a little sub note here. Any number between negative infinity and infinity. That's any real number. Okay, so the first rule, we already established it, is that, okay, if I have A to the power of N, I could rewrite it as A times A times A times A N times. So we've already got the first rule under our belts. So A to the power of N is A times A times A times A times A n times okay. So what I want you to remember is that for all of these rules, because I have an equal sign, it goes both ways, right? So in this case, it's obvious, but sometimes it won't be as obvious that, okay, well, I could expand it like this and simplify it as writing it a to the power of n. So for this next rule, for example, I want you to remember that it goes both ways, right? It can go from left to right, but also from right to left, depending on what you have to do. So if you have a to the power of m as in Matthew, I guess. I'm really bad at, I don't even know what it's called. The shorthands. I can't remember what it's called. Times a to the power of n. Is it Nicholas? I don't know. Notice here, if I'm multiplying the same base, then the second rule says that I can add these powers. So I can simplify this as a to the power of m plus n. Okay. So that's one thing that you want to keep in mind, right? Definitely, if you want to zip these up and simplify to one base and one exponent, right? M plus n is going to become something. Then that's one way to do it. Or another way might be if you have to rewrite an exponent into two powers being multiplied together like this. Okay, that's how you're going to do it. So I'm just going to do a little descriptor here. So if multiplying powers of the same base, that's important, the same base. So if multiplying the same base, okay, and I will underline that because it has to be the same base, otherwise it won't work. So if multiplying the same base, we can simplify by adding the exponents. If you have 4 to the power of 2 times 4 to the power of 6, for example, right? 4 is the base, then that's the same as 4 to the power of 2 plus 6. I don't want to, I'm not going to write that down because we're going to do some examples later, but just kind of talk you through it with numbers. Okay, so our third rule that we're going to have to memorize. So you do have to remember these rules, and they should be kind of second nature if you've done enough practice with them. So the third rule is if you have a to the power of m over a to the power of n, that's very similar, right? Now I have the same base again, right? But how I'm going to rewrite this is this becomes a to the power of m minus n. So now I can rewrite this description, right? If you're dividing the same base, okay, so it has to be the same base again, otherwise it won't work. Then we can simplify by subtracting the exponent of the numerator and the denominator, right? Or I'll just say subtract the exponents because you have to do m minus n. So if dividing the same base, and again, I'll underline that same base, simplify by subtracting the exponents. Simplify by subtracting maybe I'll say the exponent of the denominator from the exponent of the numerator, right? Throwing in more terminology here, but that's why we need to be really good at numerator, denominator, right? Because we need to be able to talk about these things. So if dividing the same base, simplify by subtracting the exponent of the denominator, that's the bottom, right? Oops, I'm not asking, I'm telling. Of the denominator from the exponent of the numerator. Remember, the numerator is numero uno, so he has to be on top, right? So that's how I had to remember it for the longest time. But you do have to remember it because we need to be able to kind of talk about math. Okay. So that's another one that we need to have under control. The fourth rule says that, okay, if I have a to the power of m, and then that's to the power of n, okay, this becomes a to the power of m times n, okay? If you think about it, this is just an extension of rule number 1, right, which said that a to the power of n is a times a times a times a times a times a times n times. Now, if we're saying a to the power of m to the power of n, that becomes a to the power of m times a to the power of m times a to the power of m times a to the power of m n times. And so you could expand those a to the power of m's. We're not going to do that, obviously. I'm just going to say it as a rule. But really what happens is you just end up multiplying. If the exponents are multiplying each other already, you could just multiply them out. So this is an extension of rule number 1. That doesn't look like number 1. Okay. So just kind of, okay, absorb it as a fact. All right, if they're multiplying, I multiply them. Okay, great, I'm allowed to do that. Kind of similar idea, similar, not quite the same, but rule number 5 says that, okay, if I have a times b to the power of m, okay, so notice that I don't have the same base here. A is a base and b is a base, and they're to the power of m, but they're being multiplied together. What I can do is, if I'm multiplying inside here, I can distribute this power inside. So this becomes a to the power of m times b to the power of m. So if multiplying, and I'm going to underline multiplying because you have to be multiplying. We'll have a look at an example where you're adding inside and it doesn't work. So if multiplying two bases, the power, or the exponent if you like I said, I use them interchangeably. The power expands inside onto each of the bases. So the power expands onto each base. Okay. So you can distribute that power if you're multiplying, also if you're dividing. Okay, remember multiplying and dividing, they go hand in hand. They're just kind of big brother, little brother situation, and then adding and subtracting they go hand in hand. And we'll actually see why multiplication and division go hand in hand in the next few in Rule 8. Okay, so just buckle up. All right, so yes, there are more rules. There are 10 rules actually. Yeah, we need to know them all. But luckily they're all kind of related. The 6th rule is very similar to rule number 5, and it says that, okay, if you have a over b to the power of m, so notice that now I'm dividing, then I'm allowed to distribute this power, but it has to go on to each of the bases. So this becomes a to the power of m over b to the power of m. Okay. So this is just an extension of rule number 5. Right, for division. And I'll underline that it's only for multiplication and division that I'm allowed to distribute inside. Seventh rule, we've already talked about actually, but it was a long time ago. It was kind of at the beginning of the term, and we were all bright-eyed and bushy-tailed, and who knows? But we said that anything to the power of 0 is just going to be 1. So a to the power of 0 is 1. And I'll just say that's a fact. Anything to the power of 0 is 1. Anything to the power of 0 is 1. Okay. So that's really important to keep in mind, because I know I see it a lot, especially in the beginning here, where you see a 0 and you just think, oh, 0 times anything is 0. But in this case, if the exponent is 0, then you have a 1. Rule number 8, how is multiplication related to division and vice versa? Well, here we go. So 8 says that, okay, if I have a to the negative n, I can rewrite that as 1 over a to the power of n. How does that make division related to multiplication? Well, if you're thinking about multiplication, then if you have a to the negative n, or rather, if we talk about here, right, this is a over b. So a to the power of 1 times b to, or over b to the power of 1. You could rewrite a over b as, using this law, right, you could rewrite a over b as a times b to the negative 1, right? And then you would be back here. You would just have a times b to the negative 1, and then you're expanding that m inside, and then you're kind of linking on all these properties, right? And so maybe we'll do an example of that in a little bit here, but so they're all related, right? And so, but this is going to be a really useful fact. In fact, I often use it going from the right to the left, where I say, okay, you know what? I want to bring this power from the denominator up to the numerator, right? So I want to bring it upstairs, essentially, is kind of how my mind works. I want to float it upstairs. Well, what do I have to do then? I have to make the power negative, right? And so if I have a to the power of n, I can rewrite that as a to the power of negative n in the numerator. So that's going to be really, really useful. And so I'm going to put a little star here. Really useful. All of them are useful, but this one is really useful. And so we can rewrite a power in the denominator as a power in the numerator by making the exponent negative, right? I said power, power, and then exponent, but hopefully the rule clarifies what I mean. So we can rewrite a power in the denominator as a power in the numerator, right? So floating it up top, numerator, by making the exponent negative. And we will do examples, so, but I just want to hammer out all these rules first. Okay. So that one's going to be really, really useful. Okay. And we combine them with the rules that we've already established to simplify things. Okay. Our ninth rule, you might have already used in other math courses, because if you want to take the nth root of something, and I feel like we've already talked about it, we might not have, but I feel like we've already talked about it. If I want to take the nth root of something, I have to do a to the power of 1 over n. So 1 over n is saying, okay, take the nth root. And I know that's kind of weird, but nth root, we write the little square root, and then if it's anything but the second root, you write the nth root inside the hook, kind of place it small inside the hook there, to the power of a. So usually we kind of float back and forth, but often in order to simplify things, I'll have to rewrite the nth root as an exponent, because then I can use those exponent laws that I have up above, right? And so we can rewrite the nth root as a power if needed. And then use those exponent laws that we've already established to simplify things. And then our last rule is kind of our pull it together rule here. Our last exponent law says that if you have a to the power of m over n, okay, so now what this is saying is that instead of 1 over n, right, I've got a to the power of m over n. So we can rework this a little bit using those exponent laws, right? M over n, I can rewrite as m times 1 over n. So let's start there. So this becomes a to the power of, oops, let's do it nice and slow, a to the power of m times 1 over n. Which by law number, which 5, right? Sorry, 4. If I have a times 1 sorry, a to the power of m times 1 over n, that's the same situation here, right? Then I can rewrite it like this, right? A to the power of m to the power of n. Okay, so let's do that. So by rule 4, I can rewrite this as a to the power of m to the power of n. And I'll just say by rule number 4. Okay. So, okay. So now what do I have? Well, now I have a to the power of m, but the nth root of that, right? And so the nth root, I'm going to write as the nth root of a to the power of m. And I can go there just by that rule up above here, right? Something to the power of 1 over n is just the nth root of that something. So this is by, so from here to here, oops. By rule number 9. Okay. It's also going to be really useful to be able to go, so just like I said, going from the nth root of a to the 1 over n, and then being able to use those exponent laws, just in the same way, it's going to be really useful to kind of rework this root, this nth root, into an exponent, and this is how you get there. Okay? So it is, I mean, it's tricky when you're first starting, right? But once you've worked with these laws, then they'll be easy enough. Okay? So you will need to memorize, and I'll put memorize in quotes because, of course, your tests are open books. So what I mean by memorize is ideally actually memorize and have them so you're kind of just using them quickly. But worst case scenario, have them on a little cheat sheet somewhere close by so you can always check and make sure that you're following the rules. So you'll need to memorize these exponent rules, or laws, let's call them. Or have them available, and you'll need to follow these rules, right? No breaking exponent rules. Okay. Let's just do an example. It is from the textbook, I guess. 117. Doesn't matter. Simplify a to the power of 4 times a to the power of 8 over a to the power of 7. Okay. There are lots of ways that we can manipulate these. They're going to follow the same theme, but just kind of the order might change. So I'm going to go through, I'll show you a couple of ways that you could solve this. Okay. Do whichever one your brain goes to first, right? So don't try to retrain your brain if your brain defaults to, right? So we have a couple of options, right? First thing I want to do is I'm going to check and see, okay, these are all the same base. Okay, so that opens up a lot of things that I can do. I've got the same base being multiplied and then divided. What are some things I could do? Well, I could simplify the numerator. And then I've got a rule for dealing with division. Okay. That's one way I could do it. Or I could say, well, I could float this a to the power of 7 upstairs, right? By making this 7 negative, right? So there are a couple of different ways that we can do it. Ultimately, you're going to end up at the same spot, okay? And they're going to feel very similar, but here, I'll make a little note there are many ways, well, not a lot of ways, but many ways. Many. There are 2 or 3 ways that I can think of. So there are many ways we could solve this. Here are 2 options. Right. They're very similar. Okay. So what I'm going to do is I'm going to do them side by side so you can see option number 1. And then here I'll have option number 2. Okay, so if I have a to the power of 4 times a to the power of 8 over a to the power of 7, that's what I'm trying to work with in each of these situations. A to the power of 4, a to the power of 8 over a to the power of 7. Side note, I think the textbook, because I have in my notes here, they've got the x multiplier. I really want you to try to move away from that, especially because if you're dealing with actual x's, it can get really confusing. So try to move away from that. Sometimes even I use them, the x multiplier, but it can get really confusing if you're dealing with actual x's. So I'm trying to avoid them. Okay, so the first option, let's say option 1, is we could simplify the numerator, right? Because I have the same base, right? I can rewrite this as I'm multiplying the same base. So by rule number 2, that says that I can add these powers. So a to the power of 4 plus 8. And then I haven't touched the denominator. I'll make a little note here. This is by rule 2, rule number 2. Just to show you where I'm getting stuff from. Okay. And then I can simplify that. So 4 plus 8 is, of course, 12. So a to the power of 12 over a to the power of 7. I didn't use a rule there. I'm just doing 4 plus 8. So now if I do, if I use rule number, which one? Let's use rule number 3. Rule number 3, let's see here. Yeah, is this one. Because again, I have this, oh, sorry, it's lagging. I have the same base, right? And so what I can do is I can subtract the exponents, right? So by rule number 3, I can use this here because I have the same base. So here we go. So this becomes a to the power of 12 minus 7 by rule number 3. 12 minus 7 puts me at what, 5? So this becomes a to the power of 5. Okay. Let's do, let's solve it a different way, right? So if your mind didn't go through this procedure, right? Let's see if maybe your mind went through this other procedure that we'll go through. And then I'll give you guys a quick break and then we'll do some more examples. So what if another thing I could do is I could just start off by floating this a to the power of 7 up to the numerator by making that 7 negative. So this becomes a to the power of 4 times a to the power of 8 times a to the negative 7. Notice how they're all on the same playing field now. So that's what I like. I always like to kind of have them all in the numerator, so to speak, all on the same level. and then they're just easier to work with. So all these rules extend to multiple bases, right, as long as they're the same. Now, let's see here. Floating that 7 to the top is from rule number 8. Rule 8 is number 8. There. So, okay. So now I can add the same, so I've got the same bases. So by rule number 2 again, right, I can add these exponents. And it doesn't matter how many, as long as they're all of the same base. This becomes a to the power of 4 plus 8 plus -7. You can see here how rule 3 came from rules 2 and 8. We're not going to go there, but you can kind of convince yourself here. So this is from rule number 2. 4 plus 8 minus 7. Okay, so 8 minus 7 is 1. So 4 plus 1 is 5. Hey, what do you know? You shouldn't be surprised. We should end up at the same answer, right? A to the power of 5. I've spaced this one out quite a bit, right? This is, so for me, this is why I like bringing everything to the numerator as long as I'm working in the same base, and then simplifying. But both of them work, you arrive at the same answer. So whatever your brain goes to, just stick with that. So I want to do, let's have a break until 11:15. I don't know how long that is. Not terribly long, but enough to grab some water or coffee or something. Break until 11:15. All right, we are back in action. And I'm not on mute, so that's always a bonus. You guys are good about telling me though. Okay, so let's do another couple of examples, right? I just want to show you that, remember that rule where we can expand the power inside multiplication or division. It only works for multiplication or division, and we'll see why in this next example. So if we do example 118, it says to simplify 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6. Okay. So if you just kind of like, I don't know, squint your eyes a little bit and just kind of have a look here, you'll see that these are the same base, right? 1 plus I, 1 plus I, 1 plus I. But I just want to throw out the warning that if we're thinking about 1 plus I to the power of 3, and if you were trying to expand this 3 inside, right, we can't do that because we're adding inside. So if you're adding or subtracting inside, you can't bring those exponents inside. So I'll even write it in red. Warning. We can only expand the power inside the brackets. Oops. Inside the brackets if we are multiplying or dividing, right? We even underlined it earlier. Or dividing inside. Okay. So, right, what I want you to notice is that 1 plus I, for example, to the power of 3, right? So if we just kind of focus on this little guy for now, right? 9 and 6 would be too annoying. So 1 plus I to the power of 3, right? We can't just expand that 3 inside, so it's not equal to 1 to the power of 3 plus I to the power of 3, right? So no, 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 because we're adding inside or subtracting, either way, right? Because 1 plus I to the power of 3, right? And you'll need lots of room, so that's why I shoved it over to the left-hand side. Well, by rule number 1, 1 plus I to the power of 3 says, well, that's 1 plus I times 1 plus I times 1 plus I. Okay, so that's why we can't just expand it. So by rule number 1, okay, so you can't just expand it inside. If we had to expand this out, right, and usually I do it, but we've got a lot of stuff that I want to cover today, so you can work through it. Just try to work through it. I'll do little dot, dot, dot here, and it becomes 1 plus 3I plus 3I squared plus I to the power of 3. Okay, which is clearly not 1 to the power of 3 plus I to the power of 3. Which is clearly not the same as 1 to the power of 3 plus I to the power of 3. Right, so just kind of remember, if you ever find yourself wanting to expand it onto addition or subtraction, so no, because you can go through and this would be a really good exercise in expanding these brackets, right? So you'd have to 1 times 1 and 1 times I. I like to do 2 brackets at a time, and then you'd have to expand it again, right? So it's quite a bit of work, but worth a shot. You know what you're doing now. So if we go back to the problem that we're actually trying to solve here, right, the key is to treat 1 plus I as one thing, right? And so I'm just going to bring this over here, copy. I went on a bit of a tangent there. Okay. So to simplify this, right, you could expand each of these out, and then that just sounds terrible, right? Think about 1 plus I to the power of 9. That's 1 plus I times 1 plus I plus times 1 plus I times 1 plus I, and then you'd have to expand all those out. No, thank you, right? So to simplify this, we treat 1 plus I as the base, right? So we treat it as one thing. So to simplify this, we treat 1 plus I as one thing, right? The base. Okay. So now I can use exponent laws, right? And so now I've got 1 plus I, I'm just going to rewrite the problem here, times 1 plus I to the power of 9 over 1 plus I to the power of 6. This is essentially the same problem that we just did, right? A to the power of 4 times a to the power of 8, I think it was, over a to the power of 7. Again, you've got options for solving these, right? Like I said, I like floating this this denominator up top by making that 6 negative, right? And so that's how I'm going to do this. But you can play around with different ways of solving this, and we should all end up at the same answer. So as long as you follow the rules. So I'm going to float that 1 plus I to the 6 up to the numerator. So I'm going to have 1 plus I to the 3 times 1 plus I to the 9 times 1 plus I to the negative 6. And just so you know where I'm coming from, you do not need to tell me what rules you're using, although it might be nice to, especially in the beginning, to justify why you're doing things you're doing. So this is rule number 8, right, where I float things to the top. And then I have the same base. So if I'm just multiplying the same base together, then I can combine those by rule number 2. So this becomes 1 plus I to the power of 3 plus 9 plus negative 6. And that is by rule number 2. 3 plus 9 minus 6 puts me where? 9 minus 6 is 3. 3 plus 3 is 6. So I get 1 plus I to the power of 6. And then I would just leave it there, right? This is actually simpler than expanding it all out. So we consider it simplified. Okay. How about another example? I want to do an example with the root. Okay. Right, where we rewrite the root as 1 over n, the nth root. So if I ask you to simplify something like, and I'm going to have double brackets here, bracket, bracket, x plus 3 to the power of 5, that's a 5, to the power of 3 over 2. Yowzas. We can simplify this, right? So, here we go, right? We can kind of tease this thing apart using those exponent laws. So first thing I'm going to do is, well, I could do a couple of things, right? I could say, well, if I have an exponent here and they're being multiplied together, well, I'm allowed to just multiply them together, right? So maybe that's the first step that I do. There are lots of ways that we could go about it, but so just rewriting it here, x plus 3. Notice that I'm adding inside those brackets, so I can't simplify them. To the power of 5 to the 3 over 2 is going to be the same as x plus 3 to the power of 5 times 3 over 2. Okay. 5 times 3 over 2 is basically 5 over 1 times 3 over 2. That's 5 times 3 over 1 times 2. That's 15 over 2. So this becomes x plus 3 to the 15 over 2. Instead of doing 15 over 2, I'm actually going to rewrite it as a root. And so let's see here. Okay. I could tease this thing apart again, right? 15 times 1 over 2, maybe that's what I'll do. Sure, why not? This becomes x plus 3 to the power of 15 to the power of 1 over 2. So now I have 1 over n, and the n happens to be 2 here. To emphasize that, I will put the 2 inside the hook, even though 1 over 2 is the square root, right? So this becomes the second root of x plus 3 to the power of 15. It's important to keep those brackets on there because x plus 3 is all to the power of 15. So you're allowed to to put the 2 in there, that's totally fine. Or usually the square root we just write as just the bare hook. We know that, right? Or the root of x plus 3 to the 15, right, without the 2. Okay. So when do we use these roots? So we need to be good at working with roots, and so going from something like this to the root version, but also from the root version to the exponent version is going to be really useful. So when do we use roots? We use roots to undo powers or to undo, same way that multiplication undoes division, subtraction undoes addition, right? And so it's just another step to solving problems, right? And so we use roots. We use roots to undo powers. Okay. So for example, if x to the power of 5 is equal to 3, and I ask you to solve for x, how are you going to do that? Well, if I told you, so roots undo powers, well then, if I have the power of 5, if I take the 5th root, let's just look at what happens there, and you'll see why it undoes the powers. So if I take the 5th root, I take whatever root the power is, I have to do it to both sides, right? So whatever we do to one side, we have to do to the other side, and that's how we're going to manipulate until we have just x left over. So we've got x to the power of 5, I'll just rewrite it here, is 3, and if I take the 5th root of x to the power of 5, I have to do it on both sides. So I take the 5th root of 3. So now I can rewrite this 5th root, right, as something to the power of 1 over 5. So let's do that. So this becomes x to the power of 5 to the power of 1 over 5 is 3 to the power of 1 over 5, right? Just rewriting that root as an exponent. Okay, so now I see how, okay, 5 times 1 over 5, well, that's just going to be 1. So, okay, so now I have x on its own, and that's why taking those roots works. So now I have x to the power of 1, right? 5 times 1 over 5, moving a little bit faster now. X to the power of 1 is 3 to the power of 1 over 5. I'm just going to leave it like that, right? X is the 5th root of 3, or 3 to the 1 over 5. On your calculator, so x is the 5th root of 3. I just want to emphasize, on your calculator, how would you solve this? How would you get an actual approximation for this, for the 5th root of 3? You would have to have, so we have to use the exponent version, right? And so you'd have to have 3 as your base. Okay, so remember, you put your base in first. And then we need to raise it to the power, so y to the power of x. And then the power has to be 1 over 5, and you want to make sure that everything stays in the power, right? And so I would put brackets around it. So then bracket, there are brackets, and then 1 divided by 5, end bracket. Wow, this got messy. Okay. And let's just see what it is approximately. It's just going to be an approximation, but let's use our calculator to find the 5th root of 3. So 3 is my base, to the power of, and then bracket 1 divided by 5, end bracket, equals 1.2457, blah, 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 right? And so, of course, if you were using this, you would have to store it because you want to keep all your decimal places. But it's roughly 1.2457. Roughly 1.2457. That's all I can remember. Okay. So, good. What if, let's do, let's do one more example before we get to logs. What if I wanted you to solve x times y squared equals x squared minus y squared for y? Oof. Okay, we can all agree there's some exponents. We've got different bases, right? We've got a base of x here and here, and we've got a base of y here and here. So if I have to solve for y, that means I need to bring all my y's to one side, and then I need to manipulate this thing until I just have something in terms of y, only y. Okay, so I'm gonna start by just kind of moving y's to one side and x's to the other side, or at least try to. So I'm just gonna write out my equation here first. I'm gonna move it over just a little bit. Xy squared equals x squared minus y squared. I'm gonna move that y squared over to the left-hand side, so I get xy squared plus y squared is x squared. Okay. Now what I can do, because I'm trying to solve for y, I've got a common factor of y squared, so I can factor that out. So I get y squared times x plus 1 equals x squared. Okay. Solving for y, right? Really, I want y, but I'll settle for y squared first. I need to divide both sides by x plus 1. So here, this becomes, so y squared becomes x squared over x plus 1. Okay. So here, we've solved for y squared, but I want to solve for y. Solved for y squared, but want to solve for y. So what do we do? Well, I know to undo a power, I need to take the root, right? So in this case, I need to take the square root. But kind of what happens is, and it's a little bit sticky, is that when you take the square root, or any even root really, but we'll stick to the square root, we have to have the positive and the negative version, because remember, when you square something, if you take -2 squared, it becomes 4, and if you take +2 squared, it becomes 4, right? And so we lose that negative property. And so to bring it back, when I take the root, and this is a bit much, I know, but when we take the root, just remember, when we take the even root, we need to have the positive and the negative version of the answer. So we can take the root, so the square root of y squared is just going to be y, is the square root of x squared over x plus 1. Okay. And I'm going to throw on the plus minus here. in front, and I'll just explain it down here. When we take the square root, I'll stick to the square root because we'll never have to deal with any other even roots. So when we take the square root, we need to consider, when we take the square, that's different, the square root. We need to consider both the positive and the negative values of y. We need to consider both the positive and negative values of y. Yeah. So we add plus minus in front of the root of the root and try to combine it into one word. Okay. Okay. So you could, right? I would consider this simplified. For me, I'm done here. You could apply the exponent laws, and maybe it's a fun exercise to do right on your own. You can apply the exponent laws and to simplify and rewrite this a little bit more. But I'm actually going to leave this here, right? I consider this simplified. You could manipulate it a little bit more. Okay, so I consider, this is me, Emily, I consider y equals plus minus the root of x squared over x plus 1 simplified. But you could use exponent laws to simplify further. And I'll just give you what you would end up at. Y equals the plus minus of x over the root of x plus 1. Right? And you might see how that falls out, right? But play around with it and see. All right, so I want to talk about logarithms, because I've got a little bit of time, not a ton of time, but a little bit of time. And so I just want to get into it a little bit before next day. So an exponential graph, let's talk about exponential functions first. So a lot of the time, money grows exponentially, right? So it starts off slow, and then once you kind of hit a large enough number, then you're making tons of interest, right? So a lot of these things have exponential growth. Also, you have to pay a lot of interest if you owe a lot of money. So anyways, exponential growth and logarithms. Okay. So in general, exponential growth looks like this. Exponential growth looks like, wow, I can't imagine what my notes, they might not make sense up above. I don't know, I can't write today. In general, exponential growth looks like this. So let's draw a little sketch here. Kind of something like, right? Okay. And so we start off slow, right? And then all of a sudden it grows faster and faster and faster and faster. And so that's what we mean when we say exponential growth. Oh, it's growing exponentially, right? And we use that in kind of regular everyday language, right? And so it's slow to start, but grows faster and faster with time. Grows faster and faster with time. Mathematically, what it looks like, so what an exponential growth looks like is maybe something like this. So mathematically, exponential growth or exponential functions have the form a to the power of x, right? So now notice that x is in the power. X is in the power. Right, that's what makes it an exponential function, is because that x is in the exponent. So to be able to solve for x, if it's in the power, we need logs. So that's where logarithms come in, right? And so we're going to have this exponential property in a lot of our formulas, so we need to be able to bring that power downstairs. Okay, so to solve for x, or any value, but let's just say in general, to solve for x when it is in the power, we need to use logarithms. Okay. Or logs. So logs, we'll talk, you might have worked with logs before, and then you know that logs can have any base. So we will only be using the natural log, which is log base e, and e is a special number, just like pi. It's but it's kind of lesser known. E is 2.71828. There's a song, but anyways, it keeps going forever, just like pi. So and it's just a constant. So logs can have any base. Logs can have any base. Okay. The most common are base 10 and base e. And e is roughly 2.71828. Right. And there's an e button on your calculator. So here, if you go to your calculator, oh, hey, I guess we talked enough about money. Who was listening the whole time? How do I get out of here? Here. So E on your calculator, let's see if I can find it here. Where is E? Oh, over here on the, see the ln that I'm holding down? Above it is e to the power of x. Okay, so if you wanted e to the power of 1, so to access the yellow menu, you have to hit the second button. Second button, e to the power of, well, 0. Forgot. You have to have the power on the screen first. How weird is that? 1, and then second, e to the power of 1 is how you do it. So I'll make a note of that on your calculator. So on calculator, e to the power of 1 is going to be 1 on the screen, and then second, And then I'll use what the menu one is, so e to the power of x, otherwise it's the ln button, and then equals. Okay, so that's how you're going to do e to the power of 1, or if you want to do e to the power of 4, you would have 4, and then second e to the power of x equals. Okay, so log base 10 is usually written just as log, okay, and it's called the common log, but for us, we're going to work exclusively in log base e. So we will work exclusively in log base e, which we read log base e, which is also called the natural logarithm. So log base 10 you would use in with things like electricity. Different fields use different log bases, but most fields use log base e. So also called the natural logarithm. Okay. And it's denoted by ln. So remember that button on our calculator that we pressed? It was the second function on the ln button, so you can see how they're related. So it's also called the natural logarithm and denoted by ln. But because I don't know, old habits die hard. In statistics, we use the natural log a lot. And so kind of growing up, I mean, in my master's and in my undergrad, we used ln tons. And so mine has gotten sloppy over the years. And so I just do this kind of script ln. And I can't break the habit. In fact, it makes it look a little bit nicer, I think. So just remember that ln is the natural log, and the ln button is on your calculator. And I am out of time, but next day we'll establish some log laws and work through some problems, and then we'll have those for when we start with simple interest. All right. If you have any questions, let me know. Otherwise, I'll see you on Thursday.